Alright, hello everyone. Got a little bit of volume there. Let's bring that down a bit. Let's see. Okay, I shouldn't be spiking too much. There we go. That should be a bit better. Alright, so a couple things I want to do before we get into things here. Hello. Yes, I worked on the Chandra X-ray space telescope before coming here. That was my shelf on my office at the Chandra. So I worked at the Center for Astrophysics at Harvard, working on the Chandra. So that's why that's up on my profile. I took a picture of my office shelf, and I got that mug, and I have my NASA mission pin somewhere. It was up on the wall in my last place. I don't know where it is now. I think it's actually in my office at MWCC. Okay, so what I'm going to look at here is just some things that I'm doing. So I'm going to flip over to the web browser in a second. And open up a generic YouTube window. Let me get that open for you guys here. Alright, now I have a playlist link which is showing up on here, this playlist of Mat 143. And so what I've been doing is I've been recording some example questions and example problems that I worked through, and some problems from different sections. I'm trying to, if I use a graphing calculator, or if I use the TI-30. If I use a table, I usually don't put that I'm using a table as part of the title up there. And so what I'm going to do is the lectures are going to be at the top of the playlist in order as we do them, and then these examples I'm going to continue to add to the playlist. Now the playlist link is, if I come back here, I go into one of these classes, in the course content, and all lectures on YouTube, there's the link directly to the playlist coming through. So I'm going to be adding different examples. I'm actually going to start doing that with the Chapter 5 material. If I can make it into here. And Pearson. Mat 143. And in the assignments, the Chapter 5 first two sections are up. So I will be using some example questions for there and posting the content. Notice it's due 2 weeks Sunday. So those examples will be coming up. It's kind of what I do in the evening. I do reply to email. When someone emails me a question, I will record a video, and I'll put, I will share that video so it's available for everyone to look at. I have noticed some of my examples go a little bit fast, so I will try to slow down a bit for those. All right, let's me get back here and move through. What I wanted to start with here is we were looking at, we had this idea of a standard normal distribution and our z-score. The thing we did at the very end of Chapter 2 became our translation for converting between the data we have and the standard normal. Because if we could transfer everything over to a standard normal, we would get the ability to read out probabilities. Indicative of a larger population, if I were to randomly grab from that larger population I would have probabilities of grabbing particular values. So that's why we do this mapping. The standard normal has a set area of probability, and we can calculate those. And the z-score becomes our thing that lets us translate between something we've observed and the probability of choosing from that, if that sample is indicative of a population. And we'll learn on finding out what makes a sample indicative of a population and when we can trust our statistics and our statistical probability to let us make that inference. So one of the things we're doing now, and this problem is we have a measurement of something. We have measured this idea that for each trip to a supermarket, a shopper spends an average of 43 minutes. Some average was made out of data. Now that data is a sample because there will always be another shopper. There will always be another shopper. And so that sample we can use to infer about large information. So if a shopper enters a store, find the probability that the shopper will be in the store for each interval listed below. When 200 shoppers enter the store, how many shoppers would you expect to be in the store for each time interval listed below? And so this kind of looks at what we do with what is the probability of one, and what does probability mean when we look at a larger population. And so I do kind of want to break this down and look at what we can do with it. And so what we need to do is, if I switch into my Blackboard here, and I'll scroll this down a bit, is I want to find my normal. I want to find the probability that we will be between 22 and 52 minutes. So 22 is less than or equal to and 52 minutes. So to do that, I need to find the z for 22 and the z-score for 52. And so my z-score is my x value minus my mean over my standard deviation. And so this is the probability we're hunting. So let's look at this problem again and go back to it. So I am looking for the probability that we're between this time interval of 22 and 52. And so I'm looking for the probability that we'd be in between these two. I have an average or a mean of 43 minutes and a standard deviation of 12. So my mean here is 43 minutes. So my mean is 43 minutes and my standard deviation is 12 minutes. Now I want to find the z-score for 22 and the z-score for 52 because that's where my probabilities are coming between. So what would be the odds that an individual would fall within this range? What is the probability of an individual? So I'm going to look at my first one, or my lower bound, so I'll put z lower, is 22 minus 52 over 12. And my calculator will take care of this for me. 22 minus 52, which is negative 30, divided by 12. And so that has a z-score of negative 2.5. And then the z-score for my upper region. Whoops, why did I put 52 in there? All right, I need to subtract by mu. That should be a 43. I was going to say that looked a little big. Yeah. So happy. Let me get my eraser out. Yep, there we go. Let's fix that. All right, always look at my formula again. So I want 22 minus 52. No, not 52, 43. Let's look in here. So my lower is 22 and my mu is 43. And I think Aisha is where I should have been the whole time around. Let me do so. 22 minus 43 is negative 21 divided by 12, negative 1.75. So we'll scratch this off, hang my head in shame, and say thank you, Aisha. Well done. But and this is our z-score formula. So now for the upper bound, I want 52 minus 43 over 12. Which is 0.75. And so now we have a z-score range. And they're related to the standard normal. This is the z-scores that would come out of a standard normal. And so what I'm going to do is I'm going to look these up on the table and find out. Now remember, when I am looking for a probability between two values, sorry, I have a bolt on the door and the dog is trying to get in, if you heard that scratching in the background, sorry. When we're looking for the probability between two z's values, we want the probability that we find, or for the larger one, minus the probability of the lower one. Well, in this case, though, those z-scores translate to 0.75, the probability of, and I'll put z equals here, and this should be x equals. I'll just cram those in, minus the probability of z equals. And so we have converted our variable x to z-scores, and z-scores we can look directly on the table. So let me pull up the table that we have on the front matter of the textbook here. We'll come back here. And so we'll come down to our standard normal table. Here's our standard normal table. And so we're going to start with our larger value, which is 0.75. So there's 0.7. And there's 5. So it's 0.7734, right? 0.7, 5, 0.7734. So I'll come back here. And so scroll this up a bit. 0.774 minus, now I'm going to, wait a minute, 7, was it 44? 7534, it was 34. So there's a 3 in here. And let's go back to the table. And so I went down to 0.7 and over to 0.7734. That gave me my upper value. If I come down here, my lower value was negative 1.75. So I come down to negative 1.7 and over to 0.5, and it's 0.0401. 0.0401. So 0.0401. And so I subtract these two values, 0.7734 minus 0.0401, and I get 0.7333. Or, as we like to say, there's a 73.33% chance if we convert it to a percentage. good. I'm glad you guys are interacting with this, continuing through. We're finding the things that we need well. This is good. And so we have the probability that an individual shopper would appear within this time range of 22 to 52 minutes. They would shop for 52 minutes. Now, what I'm going to do here is before I move on, I want to look at the second part of the question here. Not the other Z value, but the second part of the question, which is, when 200 shoppers enter the store, how many shoppers would you expect to be in for the time interval? And this is kind of how we translate our statistics. If I had the chance that one shopper would be in 0.73 times, I could do that. It would be a probability for 1. Well, if I have 200 people, each one of those gets that probability. And we can say that if I have this larger count, right, the number I expect to see is my probability times, wait, I'm going to write these the other way. Little n is usually for our subset number. And so my probability times big N. And so how many of those shoppers will I see? Well, my probability is 0.7333 out of the 200 people. And so multiply that by 200, and I should see 146.66. Well, we don't see a 0.66 of a person, so we'd probably say you would expect to see around 147 people out of 200 would be spending that much time shopping. And so this is the power of our normal distribution for us, is I can take observed data that I have observed from a sample of a population, and I can get probabilities out of it. And those probabilities tell me something about the larger population. And so we've reached the game where our observational statistics will drive us into making predictions with our statistics. I am going to put up your book lists here, and I'll just show it right now. I think using the tables are a very useful way of grabbing, whoops, that's the wrong one, sorry, of grabbing probabilities. And using the tables are a great way to pull probabilities out. But if you have a TI-84, you can look up a normal distribution using the distribution functions under the dist key. So it'd be second vars, and you would get a list of distributions. And you want to go to the normal cumulative distribution function, and you would put in your values for there to get this to work. And so what this is saying right here is that you're looking for the x value, the variable value of 100 that has a mean of 97 and a standard deviation of 25. And it finds the probability that x is to the left, which is just what our table is doing for us. And so if you don't want to keep pulling out a table and you have a TI-84, you can do this. I'm going to record some videos doing the different calculators when we need a calculator. But for right now, because we all have access to the same table, I am going to do my examples using the tables. I will record the TI-84 stuff out on the side for this particular thing. That said, it ends up being the same result and the same numbers coming across. All right. And yeah, I don't know why the slides are blurring here. I'm working on fixing that. That might be the corruption you guys are seeing on these slides. They are corrupted on my version of them. I'm putting them up as PDFs. I have finally figured out how to bulk upload to what is that thing called? Blackboard. And so I am uploading all the PowerPoints onto Blackboard. I just got all the worksheets down for one class. All the PowerPoints are going to go up tonight, and then I just need to make little links back to them. I think the Blackboard's worst thing is making the page so that you guys actually see it. It takes forever, and that has been my fight with it. All right, so we're going to start moving into section 5.3. Yes. Well, oh, wait, Bill, are you saying that it's garbled in the PDF? All right, so I'm answering Bill's question. I'm going to convert them to PDF on this end and not use the utility in Blackboard to do that. And hopefully that'll fix it. That way I can see what's going up there. They all came directly from Pearson, and I blended them, the different sections, into one chapter using my utility. I'll put the raw Pearson files up because they're directly out of a Microsoft product. I don't have a Microsoft product on this end. So I'll put the raw files up. That should take care of the garbling. And then when I create the PDFs, I'll look at it here. All right, so what we want to do is we're going to be finding values. And 1 through 4, okay. All right, well, I will keep working on them, and I'll clean them up as I go. I'm going to focus, if chapters 1 through 4 are okay, I'll just focus on making sure everything that comes from here on out is good. They're usable to a point, and we can do the material here, and I'll clean them up since we're digging into this section. What we're going to do at this point is we're going to find z-scores given probabilities. Given area under the curve, we're going to find z-scores. Then we're going to turn z-scores into the variables. Notice the last time around we went the other way. I'll use the shopping as an example. We had a 43-minute average. We found out that the 22-minute gave us a z-score of negative 1.75. Well, if I knew the z-score, if I knew the probability of a measure or a boundary, I would want to find what that would turn into a variable. And so we would look at the negative 1.75, we would convert it to our variable value, and then figure out what that means in terms of our standard distribution to what we're measuring. So kind of think of it as going backwards, right? In what we were doing, we had an average and we had a standard deviation, and we wanted to know what a certain time was in a standard normal. Now we'll have a standard normal, 2% of the stuff, and we'll still have our average and standard deviation. We'll go, well, what is 2% of the stuff? Where does that fit within what I measured? And so this is kind of the reverse of what we were doing. Mathematics, we're notorious for that, right? If we multiply, we'll teach you how to divide. If you go forward, you go backwards. Anything we do should be reversible. So, here's the book going to repeat what I'm going to say, or just said. We went from the x value to the z-score to the probability. In this section, we go from the probability to the z-score to the variable. So we're reversing the process. All right, so we want to find a z-score that corresponds to a cumulative area of 0.3632. So think about it. This was the last thing we did. We looked on the table, we got a number, we looked down our z-score column and table, and we got our probability. So to do this, we're going to go backwards. And so what we have to do is we have to look at our table on the inside, in the middle of all the material in the table. So let's look at our table here. And I come to, so I'm looking for the value of 0.3632. 0.3632. Well, down here is 0.3594, 0.3632. So it represents this value. So it's negative 0.35. 0.35. Because this is what we ended with the last time. This is what we're starting with. So if I'm going backwards, I convert it to a z-score. So it's negative 0.35. And notice here on their graph, they're showing, hey, it's negative 0.35. We're able to go backwards and find the area. And so we've now worked our way to, hey, I knew the probability, I knew the z-score. And I hope we can appreciate we've just done everything we did backwards. And here they zoom in on the part of the table, and we find the negative 3632. We look at the left-hand part of the z-score, and we look at the hundredths place digit of the z-score. All right, so let's continue this idea. Now here, we have 10.75% of a distribution area to its right. So I'm actually going to draw a bit of my normal curve. Now I'm to the right. So I have 10.75% here. But all my tables are to the left. So I've got to do something first. Well, one of the first things I'll do is, and I'm actually going to switch over to the blackboard here. So my really lopsided normal curve, I've got 10.75 here. I want to write that as, all right, hope we can appreciate that when we look at probabilities as percentages, to change them from a percentage, I move the decimal place 2 over, and this is the same as 10.75%. And so we want to look at the area, but we want to look to the left because all of our tables go to the left. And so if the whole area is 1 and this bit is 0.1075, this remaining bit is 1 minus 0.1075. So I have to subtract this from 1, which is what is that? Oh, it's like 90. Let's see, 1 minus 0.1075 is 0.8925. And so my Z value will correspond on our table to 0.8925. So I'm going to come back to our table. And I need to scroll up because it's on this side. And I want to find 0.8925. So let's see. Here's my 0.89. There's 0.8925. Okay. 1.24. And so this corresponds to a z-score of 1.24. 1.24 is the z-score. Thanks, Bill. 1.24. Right. All right. I'm going to skip the percentiles. Each percentile represents particular areas. Percentile notation, I don't personally use that often. And so P5 is saying we want the 5% place. And I just convert that to a probability coming back. I don't think I assign many problems with this, and unless you do particular types of statistics, you won't see this. It will be given to you as 5%. When we later on do hypothesis testing, the 5th percentile gets mentioned a lot. The 5th and the 10th percentile, very specific to that, and the notation is a little different. So I'm not going to obsess over this notation. Just be aware that when you see this in the book, that the P sub 5 is saying the 5th percentile. And that's what it translates for, but I'm not going to go nuts with that coming across. Let's get some clear space here, and let's start doing some things with real data then. If we can go from a percentage to a z-score, then we're going to need to go from a z-score to the x value. And so what we need to look at to do that is this equation, which we have for the z-score. It was our mu, our x, minus our mu over the standard deviation. Well, now I want to find x. I want to find this in terms of x. And so what I need to do is I need to rearrange this equation so that it works for us in terms of x. Well, if I want, I'll bring this over to the middle so I can write all my algebra steps down. If I want to clear this fraction on this side, I have to multiply it by sigma again. But whatever I do to one side, I do to the other. So I'll write this as z times the standard deviation. These will clear each other, and I have x minus mu. If I want to continue to get x on its own, I'll add mu to both sides. And so I get z times the standard deviation plus the average is equal to the x value. And so I have the ability to find my x variable if I know my z-score, my standard deviation, and my mean. And so we have everything we need in there. All right, let's continue looking at particular values then. So notice how we rearrange this equation and we have it focus on the things that we need. And the book gives it to us in this format, where we have the x value is equal to the mean plus the z-score times the standard deviation. And this works our way through. So, well, I wanted to use the example, but didn't want the answers out. So let me bring those back. I was a little quick on that. Sorry for the bit of the delay there. I've been having, last class, that person came in who was not a member of the class and just started asking a lot of questions. So I blocked them out. You might see that happen. People will periodically come into this class. I'm not password protecting or locking the class or doing anything with it. So if someone's not in the class in here and they just start gabbering a bit, I might take a second to just hide their stuff coming through. So sorry about that. All right, so let me put this question up here, and we will work them out individually, working our way back and forth. So let's get over to the Blackboard. All right, you should have a Blackboard there. All right, and so what we're looking at, we'll put the question up here. A veterinarian records the weights of cats treated at a clinic. The weights are normally distributed. It's given to us, and we'll get more about what we can get with normal distributions or not. With a mean of 9 pounds and a standard deviation of 2 pounds. So let's take that mean of 9 pounds and our standard deviation of 2 pounds. And so this is something we know about our population. We've observed this. We have sample data that tells us this. And so the first part of the question is, hey, if we have a Z-score of 1.96, what would that correspond to in the weight of the cat? Now, how we got that Z-score of 1.96, let me put you onto the browser end here and come over. So if I had a Z-score of 1.96, I would have something that would be in the 0.975, 0.960, or 0.96. Let me read it again. 0.196. So if I have a 0.196, I had a Z-score of 0.196. This was the 97.5 percentile. And so we knew something about it. It was within the 97th percentile. It should be something we know. We had this information. We had this probability. We converted it to the Z-score. And so what we want to do here is if my Z-score Z-score is equal to 1.96, how much does that cat weigh? And there's a couple different ways we can look at what this value means. We could say, for cats in the 97.5% percentile, what is the maximum weight you could see, since that is the boundary for it? This line has many different meanings in our language. But what we're going to say is, hey, X is equal to the mean plus Z times sigma. So this cat is 9 pounds plus 1.96 times 2. And so I have to retreat to my calculator. Equals 5.2 plus 9 plus 1.96 times 2 is 12.92. So if this is a mean weight for cats, and this is the standard distribution of the sample of cats, every cat up to the 97.5 percentile weighs up to 12.92 pounds. That's what converting the Z-score back to a particular value means for us. All right, let's look at this practice problem here, and we'll go from there. There we go. So, yeah. Of course, in class, this would be the time where I'd be writing everything up on the board. So that's what my pauses are. It's a bit weird in this format. You don't see me jumping through, and I don't have all my windows up yet. I think for a representation of what's going on here and take a short break mentally, I'll show you what I am looking at here. So, hello. So this is my microphone, right, by my tablet, which is what I can do writing with. And then over here is my microphone by my laptop, which will get the infinite look here, right? I have a microphone there. So wherever I talk, it shouldn't go through. I have a second screen, which is supposed to be my blackboard, but it's not working now. And so I have to like switch between window and window and window to get all of this stuff to work, because I'm only seeing it on the one screen. Hopefully, I will have the stuff up on the bigger screen that I'm drawing, so I don't have to switch back and forth. And so when you hear some of my ums and ahs, I'm switching between windows, where for you guys, I just have one button and I switch between everything else. Oh, it's not that bad, Julian. Or was the ugh my face? Alright, so I can just switch with a button between everything for you guys, but for me, I can only see one window at a time. So sometimes you'll hear me talking my way through as I'm jumping between windows. I will get that second monitor working, and then that way I won't be doing this as much, and it'll go a little bit smoothly. But I really, when I think about all the frustrations I have here, I can think in the class, when I would go to do a problem like this, you'd wait for me to write it down, because I didn't have a place to display PowerPoints without it covering the board that I was writing on. So, well, we live and learn, and we do what we can. So what we're going to do here is we're going to find specific value for a given probability. Oh, thank you, Bill. I know. I just, like, when I notice my vocal tics when I'm not comfortable. And I do realize that this is 2 classes now. I've had someone who isn't in the class jump into the stream. And so I used to work for phone company security on their internet stuff. I'm thinking, how can I secure this? And I don't want to secure it. I don't want to add extra loops to it. So I'll just do the moderation thing here and block people out and just expect humanity to be humanity, knowing in the internet sometimes it's weird. All right, so let's look at this problem. So there is a score. I'll read it in as written, and then we'll break it apart. So scores for the California police officer standards and training tests are normally distributed, with a mean of 50 and a standard deviation of 10. An agency will only hire applicants with scores in the top 10%. What is the lowest score you can earn and still be eligible to be hired by the agency? So I really want to pull apart the information we can see here. And I think finding the mean and the standard deviation are things we need to do if we have a normal. We have to find that one way or another, and I can see these right here. And then we want in the top 10%, and so that's a percentile that we're looking for. And with those 3 pieces of information, we're going to define that percentile line, or what that percentile line is. And so what this looks like is has a mean of 50, a standard deviation of 10, and we're looking for what the top 10% would be. And so we're looking for the z-score at this line, and I'll convert 10% over to that. So visually, if I'm looking at a standard normal curve, this is what I'm looking at. My mean would be at 50. I'd have one standard deviation in there, and I'm trying to find what the z-score is for this line. Is that right on that? Or not what the z-score is for the line, what the actual test score is. So what is the test score? Or the x-score. Sorry, I shouldn't call it the z-score. So, because I'll be able to find the z-score by looking at this. And so this test has a score, and I want to find what the score is in the test. So it's the x variable. So my x is equal to my z times my standard deviation plus mu. Now, I don't have my z-score. That's the thing I am not given in the problem. But because I know how much of the area of the curve is here, I can look up my z-score. I have my probability. So I have to take the probability of x being greater than, probability of x being greater than, we don't know what the number is equal to, what is the probability of being greater than this? It's 0.10. Here's where complements come into play again, though. All of my tables deal with the left side of this. So if my right side is 0.10, my left side, or the probability I'm going to be looking up, is 1 minus the 0.10. And so I want to find the z-score that relates to 0.9. So let's go back to our table. Say hello to yourselves in a browser inside of a browser. We'll go back to our table, and we need to find 0.90. And so let's see, 0.9. There's 0.9032. We're somewhere in between these two values. This one is definitely closer to it than this one. So I would use, and notice we have to estimate, 0.9 is somewhere in here. I'm only going to have 2 decimal places for this. This is 15 ten-thousandths away. This is only 3 ten-thousandths away. So this is the closer one. So I'm going to put 1.28 as my z-score. And so now I can put all this information in. I get 1.28 times, well, my standard deviation was 10, plus 50. And so I get 12.8 plus 50, or 62.8, is the score that I have to do better than. And of course I didn't hit the blackboard thing here, so let me put this back in. Sorry. I had 1.28 for my z-score. I had 10 for my standard deviation, and 50 for my mean. 1.28 times 10 is 12.8, plus that 50 is 62.8. And so the score you have to get, the score you need to be in the top 10%, is a score 62.8 on the exam. And the book goes on to say, hey, look, most scores like this are 1, so round it up. And they round it up to a 63. All right, one other thing I'm going to show here for the people with the TI-84s, this going backwards from a probability to a X value can be done in the TI-84 using the inverse normal. And the inverse normal, if you go to second and distribution, it is the third thing down. What you put in is your probability, your mean, and your standard deviation. Again, I will do calculator-specific videos with example problems as we go through. For anything I'm doing in class 4 right now, I will use the table as our way of going backwards and forwards on this. And let me... All right. That really covers section 3 in the book. And I'm going to leave section 3 there where we're going to end today. I'm going to do the next class on the central limit theorem and sampling distributions. As we get into more detail, I will post homework for section 3 and the following week up also, so that if you want to practice. I'm also going to focus on very specific calculator based videos. I know most of you are still working your way up towards the exam that's due at the end of the week. Well, I extended it a little bit because some of the Pearson outages. If you have any questions or problems with that, let me know. I'm continuing to do this material on Chapter 5. I'm posting the homework on Chapter 5, but the due dates are a little bit in the future. So I've got that our questions will be back and forth. Just continue to email me questions. I will post specific videos up. I'm definitely going to do a whole bunch of what would have been in-class examples. I usually do like 3 or 4 examples of sections 2 and 3 in class. Due to the nature of the back and forth here, I'm going to do them as small separate videos, and I'll do them around the homework. Any questions? Fire them off to email for me. What do I have on here? And we'll be starting section 5.4 on Thursday. We should finish chapter 5. Chapter 5 really is only like a 3-class period chapter, because we've done most of the heavy lifting in chapter 2, where we just set up what z-scores were. Now we're just using that equation backwards and forwards, and some tables with it. And we'll keep practicing those. All right. I will end with this shot. Thanks, Bill. You're right. My Tuesday, Thursday versus Wednesday. Yes, Wednesday we will mainly wrap up most of chapter 5 coming across, and we'll work our way into chapter 6 starting next week, which will be on a Monday. I do get the Monday right. I don't like this. I gotta do something about this. This is my quarantine beard. Remember, email if you need anything. Alright, I'm going to put the sound off, because as soon as I put the sound off, I can